Yes, hello. I hope you can hear me. I'm Karolina Jesionkiewicz, Niedzinska, and together with Dr. Andrzej Brzeziński, we've prepared a presentation for you. And it, in fact, is a continuation of the previous presentations by Dr. Brzeziński. So when you look at the situation in Poland, you'll see that general strategy papers in Poland are quite clear about the objectives, which is to increase the share of cycling for day-to-day trips. But to make this possible, we have to have pretty detailed guidelines. Their objective is to make the infrastructure easy to use and convenient, but first of all, it has to be safe. So what I'm going to focus on are several new additions, and they are new when it comes to cycling, because obviously it's not that new for cars. But I think that this is really important when designing cycling infrastructure. So in the draft design guidelines, we have a new term which is called speed to be designed. And that's an important idea because it really determines the kind of solutions and parameters we will adopt, and it adds clarity to our solutions. There are some other elements there, and providing more space, widening of bikeway curves or the clearance. And finally, I would like to talk about visibility within points of collision. So, what are the particular or special features of cycling? There are three ranges of speed that are important for cycling and for designing cycling infrastructure. Up to 12 kilometers per hour, the cyclist cannot ensure stable traffic. Anything between 12 to 25 kilometers, that's the speed at which an able and adult cyclist goes at. And anything above that is not just because the cyclist has a better cycle or is more able, but the gradients may differ, or the weather. And so we ran a study, a gradient of 2%, and wind blows at 16 kilometers per hour, then the cycle speed can go up to 40 kilometers per hour. And so considering this, plus international experience, it was decided to introduce 4 speeds for designing cycle infrastructure. It's the minimum speed, 12 kilometers per hour, and it should be applied to special situations where we plan to stop the cyclist or when there are some constraints regarding the area. But we should really apply 20 and 30 as the general speed, but in special cases this could be up to 40 kilometers per hour. And as you've heard from Dr. Brzeziński, there are some specific situations where it's okay to use these higher speeds. The next element in the guidelines is the specificity of how cycles of cycling on curves. And we know it from studies that when a cyclist goes down or up a cycle, their inclination is at the maximum 15 to 20 degrees. And that's a result of the speed for this cycle road and from the radius. And using these two, we know what the angle will be. And if it's anything above 20 degrees, this means that the cyclist is not going to reach the design speed, and instead it will be lower. And once the theta angle is below 20 degrees or some 15, can we then design for a wider lane? And that how wide that lane will be depends on the curve, and also it depends on the clearance zone. So we calculate that using a specific formula. Well, any widening of those zones can only be applied to cycle roads, but when there are no elevated obstacles to the sides of the roads, then we can widen both the cycle road and the clearance zone. Here is an example of what the widening will look like under extreme situations. So we have the design speed on the left-hand side. In the middle column, it's the curve radius and the widening value. As we can see, the maximum value of widening is not bigger than 65 to 75 centimeters, and that's because of the angle of how the cyclists lean sideways. There is also an assumption that when the cycle road within the curve is really wide, then we don't have to add any extra widening because the road itself is already 3.2. Right, when planning cycling infrastructure, we also have to plan for solutions for points of collision. Well, obviously it's important because such points of collision determine the speed, and the more frequent the stops are, the lower the average speed along a route. But it's not the only reason why we have to focus on this. These places are potentially hazardous for cyclists, different cyclists. Please remember that we have a wide variety of cyclists. And when we define the values for visibility, we assume that over a distance which is equal to the stopping distance, then the cyclist should be able to keep an eye on the point of collision so that they can adjust the speed accordingly. If they can see an oncoming vehicle and they don't have priority, then they will not accelerate. Instead, they will slow down. So considering this, the LD value, which is one of the arms of that side distance triangle, this has to be determined using the design speed for cycle roads. And there are three groups here. We assumed that at points of collisions, we cannot assume that cycle traffic will be at 30 to 40 kilometers per hour. Instead, we think that points of collision shouldn't be at more than 20 kilometers per hour. So that's group one. This is followed by another group at 12 kilometers per hour. So yes, this is still smooth traffic, people crossing that point of collision. And finally, cyclists coming to a stop. So the length of LD is also affected by the gradient. And here again, we assume that the gradient shouldn't be higher than 6%. And this really is the result of the big changes
I mean, the higher the gradient, the more it affects the stopping distance. Moving on, the LW value, considering the speed of the vehicle. This is how we determine the distance LW, but cycle speed is equally important, but we've split this into two situations. Well, the first situation when the cyclist has to stop, and the other one when they can drive across the point of collision without stopping. And obviously, we also have the gradient included here, whether it's close to 0 or whether it's 6%. So LW here is really similar when you look at where the cyclist has to stop before the point of collision or when they are allowed to cross that road without stopping. Well, when a cyclist stops, they need some extra time before they can go back to the original speed, before when they take off from the 0 point. Now the conclusions. The changes have been proposed to the draft design guidelines. And their objective was, first of all, to ensure that there is consistency throughout the design process. What we want to achieve is to ensure a constant design speed along the whole route. Cyclists, as they go from A to B, they can use a variety of different routes consisting of roads and lanes or dedicated roads. At the end of the day, the idea is for all these elements to be cohesive, consistent, which should support the design process. But all of these elements have to be met, and safety comes first. And my final conclusions. What the regulations can actually do is be very open about what the standards are today. But what I don't want you to think is that cycle infrastructure should be designed for 40 kilometers per hour. Instead, what we really want to achieve is to raise awareness about what the actual parameters should be, so that the objectives set out in the documents should really be achieved. We have to follow the parameters in an informed way. So if we design the speed for 30 kilometers per hour, then we have to ensure the right radiuses, the right widening, or any extra space if needed, etc., etc. Thank you.